Good morning, everybody. Now, there we go. Now my microphone's working. Okay. It's a beautiful Saturday morning, and we're gonna be OS coding. I'm just having a little bit of banana and Nutella. I love this shit. I took my daily vitamin gummy. I'm having milk in a wine glass. And I'm gonna be coding my OS. So, let's get to it. I left this note here that the walk table function doesn't really work. Let's take a look at the walk function here. Oh. Dude, come on. The walk function. RISC-V SV39 scheme has 3 levels of page table. 512 64-bit PTEs is split into 5 fields. Okay, it is using calc. So F, PTEV, and what is V? PTEV. So essentially it's checking if PTE, that page table entry that is seeking, if it doesn't exist, it creates it using calc. Creates a page for it. I wish I had some music. Anyways, PTEV, who's defining that shit? It's in RISC-V.H. PTEV, valid. So it has a valid flag. 1L, 0 shifts. What does that mean? Why 0 shifts? If it's just 1, don't shift it. Stupid. Hey. Valid. That's the first bit. If the first bit is 1, that means it's valid. What if it is accidentally 1? And it's not valid. Then what? Yeah, then what? You know what? I'm gonna change the structure of my memory. Right now, when you're freeing up a space, free range, okay, free. So when you're freeing up some space in memory, it's adding that space to the end of my stack thing. It's kind of like a point. It's kind of like a linked list with a pointer. But what it's doing is that putting that yeah, it's like starting at the end of the memory, going back to the beginning of it, which is a bit weird because the first page table that I'm allocating is my kernel's page table, and while I'm running code, it's while I'm running code, it will be trying to allocate some stack pointers to variables. That's not good, because then those variables will be overwriting my page table because they're in the same location. For that reason, I'm going to try and add freed memory to the top of free mem first. I'm going to try and reverse that process. Like, okay, free list. So the opposite of what's happening here is kmem.freelist. Oh. Free list. Next of that is R. And then set R to be, that makes no sense. That makes no sense, dude. Let me think. So we have that. It's next is free list. Maybe I could just go backwards here. So when I'm doing free range, start from the end and go backwards. Here, say start and turn this into end. Will that still work? Let's see if it works. I'm not sure. Excuse me. What am I doing, LS? Break. Main. Continue. Oh. Init MMU. That happened really fast. How did it happen so fast? Oh. That means it's okay. It's facing an exception. Run the code again. What am I doing wrong? Am I accessing memory that I'm not supposed to be accessing? Oh. I'm going overbound. This should be a minus. Break main, continue, next. Still, I'm fucking up the memory. What am I doing wrong, dude? It must be there. So I'm setting the pointer to the end of memory. Oh, so did I... If it's less than or equal to the end, okay. Then here, we actually don't want to we want to do p minus equal page size ones. Yeah. One. We don't want to start at the boundary of the memory. I'm going to start at one less. So that when we dedicate a page to it, it doesn't freak out. It doesn't go over bound, dude. You hear what I'm saying, man? Oh, fuck. Okay, let's not do that. Let's find another way to fix this. I'm done with the breakfast, I swear to God. Gotta have the energy to code, right? And also, if you code a lot, if you stare at a monitor a lot, get one of these. You gotta get one of these, man. It's a blue light filter, blue light UV stuff. And it helps your eyes not get fucked up, because sometimes when I code a lot, I get fucked up. Sign up for the course, excited AF. Hell yeah. I'm working on the first module right now. How's it going? Hey, welcome. Transistor of today, that's a nice name. You're into transistors? 0.7, am I right? If you know what I mean, you know transistors. Anyways, let's go back. P plus page size. Okay, I want to reverse this process. What I'm trying to do right now, it's when I call free range, it starts at the start and goes towards the end, one by one, freeing up spaces in the memory, adding it to the kmem, the free list, to the free list, so that we know which parts of memory are free to use. But then, for some reason, because I don't want it to collide with my stack memory in the beginning, I want to reverse this. Instead of going from start to the end, I want it to go from end to the start. Because the way it adds those free spaces to my free list is in reverse. If you know transistors, coding is easy, dude. Don't worry about coding. You get it. You get it right pretty soon. Okay. So R set a next to my free list, and then pin that on my free list whenever I'm opening up space. I'm setting the pointer to what I already have. If I want to reverse that, is that when I free up some space, I set the pointer of this one to that. But then I have to, in that case, I'll just have to walk the entire free list to find the last item every time. That'd be very stupid. Yeah, the only way is to reverse this process here, which starts at start. You wanna start in the end, at the end instead. So end minus page size. That'll be my pointer. And then every time, oh yeah, we gotta keep that. That's stupid. Don't change that. You go on an infinite loop though, that way. P plus page size. Okay, I don't know how to solve this. I don't actually need any of these. Whoever calls free range, it's free range. Who calls it? Free range then. Memend, instead of memend, use memend minus minus page size. So we could leave one page for my stack pointer. Just leave that there. And then when you're freeing up things, instead of setting everything to 1, let's set everything to 0. Alright. Oh, okay. Oh, whoa! It was running all along in the background? No wonder my PC's going crazy. Jesus, dude. Jesus, man. Drinking milk. Target remote 1 2 3 4. That's a port. And then break. Okay, page init malloc map pages 31. You don't want to break there. That might be even. That might even be why we're getting thrown into an infinite loop. Continue. Gotta wait for the thing. Free memory. Okay. There we go. Beauty. Beautiful. Print X. Wait, what was it? 16XW. And page table. Letters are what? That's super weird. AC, BC, CC, DC. Why are those addresses there? Why do I have that there? Isn't that the address of my page table? A70 FD4B0. Why is it there? Am I checking my stack? Oh, okay. Oh, right, okay. Okay. I know what I'm doing wrong. When I'm using calc. Where's calc? Where are you, calc? Come over here. Get your ass over here, calc. Malloc. I don't have a calc. Calc's for Unix. My malloc is setting things to 1. That's what I'm doing wrong. You just need to set it to 0. Because when you're creating a new page table, you don't want values in there. You want everything to be 0. If there's values in there, that's going to confuse your page table. Am I right or am I right? Or am I wrong? Because sometimes I'm really wrong. What was it? Map pages. Freeing up memory. La la la. Come on, dude. You're so slow. Oh, never mind. It stopped there. So now if I print, X 16 XW and page table, it's all 0. Great. That's what I wanted. Now that means none of them are initialized. And then in that case, I gotta check if when you're walking, when you walk table, you get the address of the next page table. So now we need to check the address, check the table. If it doesn't exist, or if V isn't 0, isn't 1, create or just malloc. That means check the table. Okay. So that's if table and 1. If that's not true, that means it doesn't exist. That means you do your thing. You do your thing, dude. You do malloc. At this point, I don't have any boundaries for, so to do add kernel panic. I don't have a kernel panic at this point, but it should be alright because I'm not using that much memory anyways. uint 32 malloc just allocate 1 page put in T, and if table and 1. Yeah. Do I need to cast this? 1 is 1. Doesn't matter if it's unsigned or not, right? Uint. We get the T. Set T equal to malloc. What else do I need to do? PT void. I'm getting the value at that address. Oh, we need to do this. Before doing that. So get address if table address that can't be right. If table that'll access it. Right? Let's put that in another uint32. Let's call it temp for now. So if temp is 0, that means it's working. 32 malloc. Wait. I actually need to do that. I'm very confused. I'm just gonna run it once and oh, wait, what? uint32 from void. Oh shit, what am I doing? From void. I'm creating an address. That might be really wrong and stupid. Let's see. There's no way of knowing unless you run it. Right? Map. Oh. Walk table. Funny thing is that when you're running GDB with it, it takes so long, but when you're not using GDB to clear up the memory, when you're not running it with GDB, it happens instantly. So I'm guessing everything has to go through GDB when you're running GDB. Through some sort of a pipe. A pipe up. Next. You get the address. And then you get the temp. Okay, now print x table. That's the address of the page table. Address is 0. That means it's not supposed to change. How's the address 0 though? That makes no sense. It's not. There is a 1 somewhere in there. Am I doing that wrong too? I think I might be doing it wrong. Dude, you're not supposed to shift left. You're supposed to shift right. Oh. Anyways, just let's make sure the other parts are working. But I'm gonna forget that. Shift right, stupid. Print x. Instead of the address, print temp now. Temp is 0. So that if statement is going to be 0 and 1, which is 0. Flipped, it's going to go in. And then do malloc print x temp. Now temp is fcd4, which makes sense. It's 1000 in hex, 1000 away from the last address. 1000 more or less, is that DCD? Okay, 1000 less. Just going backwards. That makes sense. Now set table. That looks like old code. Didn't I change that? Why am I so dumb, dude? First of all, shift right. Am I right? Am I right? Am I right or am I right? I am alright, I am not alright. PX, where's PX? PX. Where is it? Oh, this is VM, not VM. Risk V. PX. Yeah, it is shift right. Shift right. What was I thinking? And here, instead of doing temp, you set. Yeah, I am supposed to put temp. Okay, let's try again. Oh. Walk table. Continue. We'll wait for a little bit. A little bit of waiting. A little bit of waiting. Okay. We're here. Next. Now, okay, print temp is pointing at the new address. But what is address? Print is address. It's not 0, it's 40. Okay, good. And then if I press next, table's going to be moved to the new point to the new. Oh, There's a burp coming to point to the new page that I dedicated to it. So n print table. What? Why is it 0? Dude, why is it 0? It's not supposed to be 0. Why do you go to 0 again? Oh. I thought, man. PT. Okay, let's see. uint 32t pt print. It's a page table, right? And then we go 0x40 what's in this here? It's 0. And what's in temp? I thought it was pointing at the same place. Whoa, okay. I'm doing something wrong here. Why did that run 3 times? That's worrying too. Oh, that's why. That is definitely why. Table of address. Oh. Before anything, if you don't run it with that, it's gonna do. What? I was crashing so many times. Oh yeah, I get it. It's supposed to crash at this stage. Run it one more time, baby. Dude, no. Don't run it like that. Run it with SS. Target 1, 2, 3, 4. Break. Walk table. And then we wait. 38 minutes in. It's 0. No, it's not. Okay. That worked. Now we go next. The next address Yeah, okay, we gotta repeat the same thing for this part too. Here. Get the address. Get the PTE. If there's nothing in if the address is not valid, you need to malloc, create a new page. And then that PTE, the table address, yeah. It'll be pointing at that new page. PTE. And then returns that page table entry. It's not a page table entry though. That's the wrong name for it. Like it should be, right? Should I return a page table entry? If that's what I'm doing, in that case, I don't need to go through with the second level. I just need 2 levels. That's why it was 2 levels on that. I need 1 level. It was 2 levels on that XV6. That makes a lot of sense. Yeah, okay. Now that will walk the table and return a PTE. And then after you have a page table entry, this might be stupid. No, that's alright, it's alright. We're gonna suppose that, okay, map pages, oh, wait. If the VA is already taken, map pages doesn't check and overwrites it. So be careful, guys, when you're using this OS. There's so many ways it can go wrong. Create a mapping from VA to PA. Wait, what? What did I do? Create a PTE, or just get the PTE. What is PTEP? Once you got the PTE, oh. That's a pointer. You could do PTE. Wait. Am I doing that right? Yeah. We could just put, we could do a malloc of size 1, create a page, or give it the size. Do a malloc, give it the size, put the address in PTE, which is stupid because we need to change that. The address needs to be shifted. PTEs are not. They don't work like that. Where is it? A PTE. it has a PPN and flags. What are the bit sizes on those? PPN 1. PPN 0. That one's 10 bits. The other one's 12. I don't get it, dude. 10 and 12. That's 22 bits. Yeah, so 22 out of 32, 10 of it it's as flags. SV32. Let me search it up. SV32. Good. So 8 bits plus 2, 10 bits of flags. 10 bits of flags. I need to fix that. How will that point to a place in the memory though? With only 10 bits. Zero. Page table entry. I'm having trouble understanding this. Hey, how's it going? Welcome. It's a nice Saturday. Just sipping on milk and coding OS. Do you know anything about page table entries? I'm having trouble with it. Like, okay, this is a page table, right? The first 10 bits are flags. And then the rest, which is 22 bits, it points to a physical page in the memory. But how? It's only 10 bits. How can 10 bits point at you need 32 bits for that? So you're going to be missing a bunch of parts in the memory. You know what? Whenever you're stuck, you gotta ask ChatGPT. Explain SV32 paging, please. There's no tomorrow. Only today. I wish there was no tomorrow so that every day would be Saturday. That'd be awesome. Would you agree? Virtual memory concept in SV32. Virtual addresses are translated to physical addresses using a structure called page table. SV32 VPN virtual page number offset 2-level page. ChatGPT doesn't explain that because sometimes, man, you need GPT-4 for a better experience. I do have GPT-4. GPT. I agree, though. GPT-4 is a lot better. It's a bigger size. Bigger size model. 2-level page table. We got level 0, level 1. This level uses the VPN1 portion. Okay, the entry found in the page directory using VPN1 points to a second table. VPN0 is used to index this. Okay, now we have the PTE in the end. Each entry in a page table includes several bits that provide the physical page number, PPN, and control bits like valid, read, write. Okay. Translation process. The physical memory uses VPN1, VPN0 for its physical page address. Address size. The SV32 model supports 4 GB of virtual address space. By the way, new subscriber man randomly found your live stream. Whoa. Oh! Did you just come across my live stream like out of nowhere? You hadn't seen my videos before? Imagine we have the PTE in the end. Oh damn, welcome. I'm gonna check out your channel. I forget what I was doing. Now imagine we have the PTE in the end. SV32 model supports for you wherever we tried. Address space. We have. Yeah, let's be friends. Just don't act suspicious. I've had people dropping in my streams before. I don't really need that. But if you enjoy Coding OSs, you're welcome. Now imagine we have the PTE in the end. 10 bits of it are flags. How can you address the physical memory with only 22 bits? In SV32 page model of RISC-V, 10 bits for flags control purposes. I have 32 bits PTE to 10 bits dedicated flags. That's what I said. These 22 bits allow addressing of physical pages. 22 times 4 kilobytes. The page size. I'm really confused. You could prove to me that you're not like others by helping me code my OS. If you don't know OS stuff, and if you're not a programmer, that means my channel's not for you, man. Physical page number. Page offset to get full physical address. Alright, I was forgetting about the 10-bit offset that we had in the beginning. Look at that. Wait. Page offset is 12 bits. 12 bits of offset. But we have 10 bits of flags. 10 plus 12 bits of offset is too many. Too many bits. Right? 22 plus that's 34. That makes no sense. 22-bit PPN. 12 bits of virtual address. So if the offset is 12 bits, the PPN is 22 bits. That sums up to 34. That's too many. Isn't that too many? Correct explanation. You're right to point out the inconsistency. Let's clarify how 22-bit PPN fits within the 32-bit address space. 10 bits for flags. 22 bits for PPN. Flags. Why are you explaining it over and over again? The console 32-bit system uses 4K pages. The full 22 bits are used solely to directly address the physical in a flat manner. Here's the key detail. Give me the key detail, dude. PPN 1, 10 bits. PPN 1? We have multiple PPNs? PPN 1, PPN 0. Alright. Oh. And what do you use that for? Why are they 2 PPNs? And still 34 bits. Total PPM bits in use 22 bits. This represents a 2-level split, allowing for more nuanced control and addressing within a potential larger physical address space. Damn, nice trick. Nice trick. So now, if you're using 2-level PPNs, you can have 34 bits of address space. Instead of 30, so on a 32-bit machine, you have 34 bits of address. That'll allow for a bigger RAM to fit in your RISC-V system. It is genius. God damn. It was very confusing to understanding, but yeah. There are no good references to understand RISC-V. There are books with a lot of rambling around. But now that we know, okay. Let me take off my glasses. I'll probably be okay. So now, shift right stupid. Yeah, I already did that. Let me remove this. Page table if V is in that, and then we have the page table entry here. Before that, we on each PTE. Where's that? My temp address. I'm just doing that once. Malik. Okay, I'm still confused. How does it work for the first level? For this one, VPN 1 is 10 bits. First level page table. Do we still have 10 bits of flags in the first level of PTE? At each level, the page table is standardized, including how many bits are used for flags. Let's clarify the breakdown for both. I know the flags. Bit allocation in PTE, PPN bits. But I have a 32-bit address. How do I fit that in a... This is really confusing. Let's take a look at the source code of the Unix. Maybe the answer is here. Maybe it's easier to see it here. So here it creates a page, memset. But this is 64 bits. That's not going to work. That's not going to help. VRWX. You gad. Oh my god. If you have around 8 to 10 bits used for flag, this leaves 20 to 24 bits in the PP in practical terms. How do you walk the page table in SV32? How do you determine the address of the second level table? Give me an example. Oh! What's up, dude? Activating Hyperprogrammer. Hyperprogrammer mode. Hyperprogrammer mode activated. Dude. I don't know if I have the energy for this. Find a physical address. We've got starting point. Boom, 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 boom. Example. Okay. Break. Physical address, virtual address that. So we go to virtual address. That's VPN 1 is 011. Oh. First level indexing. It's calculate address plus that times 4. What's times 4? Page directory add that. Okay. The indexing times 4. It lands there. Assume the PT at this address indicates a second level table store set. What would be the value of PTE in that address to be pointing at 0x881 bing bing 1 2 3 4. Oh. You just drop 3 bits of it. 3 times 8. 3 times 4 is 12 bits of it. And you're left with 20. 12 least significant bits offset within the page are not part of the PPN, as the PPN only includes higher order bits, hence why 12? Right, because there's 22 bits. 34 bits. This is really confusing though. Like I understand it now, and I have to code as fast as possible before I forget how it works. I'm forgetting. I'm forgetting it. Dude, I'm forgetting. What was it? Fuck, I forgot. PT. Come on. Yeah, so. Shift right for 12 bits. Drop the first 12 bits. You set that to there. You grab the PTE, you return it. Now we're talking, okay? Yeah, I gotta write an explanation for this 12 bits shift right to drop the first 3 X digits. Because PTE plus offset is 34 bits and 10 bits are flags and a PTE. So to replace a 32-bit address back into 34 bits, we shift right 12 times and then add 12 offset bits later. Was it 12 offset bits? I guess. Only on the last level. But PTE everywhere is the same. So this is really confusing. But anyways, we know how it works now. We shift right 12 times. Drop all the bits. Shift right 12 times. We're not supposed to shift right 12 times though. That's just a PPE. We just need to end it with 32-bit F. No, FFF. Here, FFFF. End it with that so that we know that that's available now. Keep the address there, the 12 bits of address, and then drop everything else in between the flags. Hey, what are you working on today? I'm working on my OS. We're still doing memory management. Memory management is not complete, but once I'm finished with memory, I'm finished with my operating system basically. It's called a very tiny OS. As you can see, you might be able to read it. It says very tiny OS. That's the name of the operating system. And then after I'm done with that, I'm gonna finish the articles, and then when I'm finished with the articles, I'll publish them. That'll be the first module of Core Layer. Core Layer, baby. I wonder how many people have signed up on Core Layer. But yeah. Core Layer, dude. Whoa, why is it? What? I'd never tested it on a big monitor. It doesn't work on a big monitor, apparently. That's funny. I didn't know that. Like, it's all centered here right now. If it's a small monitor. By the way, I need to change the roadmap, because the operating system has to be at the top. Now, intro. Okay, first article is going to be intro to RISC-V, and then the second article is going to be operating system. The third one is going to be just coding the RISC-V in machine language. An actual OS. Damn, that cool. How do you even make an OS? You what? Wait. You have... Is this your first time on my channel? You haven't seen my channel before? That's what I do. I code OSs. Or at least I've been doing that very recently. For the past few months. Yeah. Because I'm putting together a course. Is this actually your first time on my channel? That's weird, because you're the second person who's like that today. But yeah, anyways. Before I forget, we've got K-page init table. Okay, now that table address is being set in the right format, got malloc free range. Now that map pages is working, is it? Am I right? Map pages. It is grabbing the PTE there and then doing malloc. Okay, when you're doing malloc, you still want to do 12 shift right, or not 12 shift right. I just end with that. They have that PTE, and then addresses are going to be offset by their offset. And then the PTE pointer, we create a pointer from it. Offset and put PA and with the same thing in it. There we go. There we go. You've seen some of my challenge videos. What challenge? Challenge videos. I have challenge videos? Goddamn. I didn't know that. Like my old vlog videos? I was doing daily vlogs for some while. There's a day 7 of coding or something. Oh, right. Yeah. I stopped doing those a while ago. It's not a challenge. It's basically the same thing. But then I realized that it could be valuable to people, and I turned it into a course. And stopped doing daily stuff. Because when you do daily vlogs, you it's kind of hard to come up with interesting stuff on a daily basis. So I just switched it to not daily, and I post whenever I'm ready, and whenever I actually have something to make a video about. So yeah. Now our memory map pages, that function there is working. So it's time to map the PLIC. Wait. We might not be using the size here. Okay. Map pages. And we're not using the permissions to set the flag. Size here. The website, I'm gonna drop it here. Oh, my bad. How can I remove that? It's so annoying. It's not that though. Yeah, remove. Sorry. That was a mistake. HTTPS corelayer.pro, because the .com was way more expensive. Don't tell anybody that. That's the website. I'm gonna pin it. Why is it so hard to pin shit? Dude, just pin. Awesome, we have a pin message in our live stream. Wait, what are we unpinned? Pin message, hell yeah, dude. Okay, now I'm not using the size element here. Malik. I'm not sure how that malloc size works. But first of all, let's fix the allocation. So when you say amount, you have to allocate for the amount. How? For int I equals 0, I less than amount, I plus plus. I wonder how many for loops I've ever written in my life. You mem set to 0. Whoa, how was it done again? Let me take a quick peek at calc here. Calc. Where are you, calc? Calc void. Huh? What? VM map pages. Map pages. Do you use calc size? Where do you use that size? VA plus size minus 1. And how do you use that last? Oh, this is really complicated, dude. Why did you call it A? A plus page size. Oh, so you just keep allocating pages. Until the beginning and the end are the same thing. But first you have to align them. How does that work? Page ground down. Page size minus 1. It's 49.6. So if you would do minus 1 and then not, it'll flip all the bits. of your page size. So wherever it's 1, it'll be 0. You know what? I'm just gonna copy that. I won't tell if you won't tell, okay? Life's easy. You don't have to torture yourself. If you don't understand it, just try and copy it. If it doesn't work, then you go understand it. Map pages. For PLIC, what's the address of PLIC? PLIC base address. For PLIC map pages, page table. Dude, page table. PLIC base ADDR. Map it to the same address. And what should be the size? Permissions need to be changed, okay? So to do set perms right. Just subscribes. Love the F12. What's F12? Thank you for subscribing. But what is F12? F12 button? In course? Love the F12 in course? What's F12 in course? F12? Alright, F12 for I see. Dude. Yeah, totally forgot about that. That's a weird way to sign up. Did you try and sign up? Could you? No, no worries, man. I should remember what's going on my website. Got the page table, PLIC base address, PLIC base address. Okay. Now for the size of PLIC, I need to look this up. For the size of PLIC here, what's the biggest number that we're adding to PLIC? We can ask ChatGPT, right? You could trust ChatGPT with the size of PLIC. Let's calculate it. What's the size of PLIC in RISC v32 in pages 496 byte pages. Platform general consideration for PLIC say a larger number of interrupt sources. Priority n times 4 stealing 4096 bytes. Conversion to pages. See, it's saying 2 pages for PLIC, but I'm pretty sure I saw a crazy number map pages for PLIC. Map pages. Go back to the top, baby. Map pages. Who's mapping the PLIC? Page table T. The only place we're calling map pages is in process. Map pages, page of the trampoline. That's for processes though, it's not for PLIC. Is it here? Map. There's no map pages here. My NeoVim theme, I'll show you. I'll show you in just 1 second. Let me just solve this. But we have more usage of map pages here. Map pages. Load user init code. Map pages. This is the definition. KVM map. I don't get it, dude. What's here? Yes, let's my theme on here. Maybe I should switch my theme. Well, so it's I'm guessing it's aquarium. Oh, yeah, it was an aquarium. Looked like this. Euro. Let's see if I find something more interesting. Ooh. Oh, shit. Oh, fuck. Hurt my eyes. They all kind of look the same. Ooh. Ooh. Brother, ew. Ooh, I like the colors on this one. Is that too bright? Because I have a bunch of definitions. I don't know. Let's keep that for now. I'll switch if it's too bright. Yeah, I still don't know. Yeah, okay, it's here. PLIC. Whew, that's the size of PLIC. That's how much the KVM map. That's how much they're doing. The Unix system is dedicated. People who use light themes should be thrown in jail. I don't know who uses light themes. Who uses light themes? Does anybody here actually use light theme? Not a light theme user, but I know light theme users. Some used it because it was more familiar coming from Skype. Dude, what the fuck? Coming from Skype? Wait, it's talking about Discord. Yeah, that's not what I'm looking for. Why do people use light themes? It's the most natural to people. Oh, I don't know, man. I think I used light theme once. To be honest, Okay, the right light theme might actually be better in the morning. Like, that is too fucking bright, dude. I know it's light theme, but it doesn't have to be that bright. Those are all my light themes. Like, this one might be kind of nice. It just does not feel right. It doesn't matter. Themes don't matter, man. What you code in does not matter at all. What you code does. William Wilson, the genius of computers, said that. I used light on Notepad Plus, but once you use dark, there's no going back. Notepad Plus? You used Notepad Plus? Why did you use Notepad Plus? Who uses Notepad Plus, dude? I knew this guy who was really fascinated, but Notepad Plus Plus, use it all the time. It's like, oh, this is so cool, and I hated that guy. He was like one of those guys who are crazy about design patterns and clean code and having enterprise libraries designed for the company, and I hated his guts. Because every time I wrote code, he'd come up to me and be like, why didn't you use this library that we wrote before? Why did you use the fucking things that C# gives you? And Microsoft actually put in C#. Why did you use Microsoft stuff instead of my stuff? I was like, dude, Microsoft stuff are better. And he actually deleted my code and rewrote it again on his own spare time. My code was faster, by the way. But yeah, he used Notepad++. Are you him? Did we work together? I'll get one. Oh, dude. Okay, free range. Okay, edit. I'm getting really tired of this. It's just, okay, KVM map is just mapping, but it has a panic check. It does use the same thing as size. So for size, it is using 4,000, if I'm not wrong, or 400,000 in hex for PLIC. That is crazy. Why? Well, let's ask ChatGPT one more time. 2 pages. Huh. What do you have to say about this? This is from Unix source code. Huh? Huh? ChatGPT, what do you have to say about that? You said 2 pages. That's 400,000 pages, though. In hex, it's a lot more pages than 400,000. It's just 1 megabyte. Oh, my bad. 256 pages. Ow. Okay. That's just to be safe. Yeah. So, wait. For PLIC, we do 0x400,000. That's 1 megabyte. Oh. And also, let's see. For UART, it's using page size, not one. So I'm using one. That makes no sense. We need to change it to page size. So 1 page, 1 megabyte for PLIC, and then map pages needs to use that size thing there. And I'm just gonna fix that, and then I'm gonna take a break. I've been streaming for an hour and a half. No, it was my first time trying programming, and Google lied to me that Notepad++ is a popular text editor. So I used it to write HTML for a week, then used Sublime. Ooh, I remember Sublime. Sublime. You must be really old. Fuck. Sublime 3. I had this friend who was really proud of using Sublime. I used the first editor, the first thing I ever coded in was Visual Studio. Not Visual Studio Code, Visual Studio. It had like a crazy amount of setup. It was like, I don't know, 10 gigabytes. And I coded in C in there. Wait, I first coded in JavaScript. And something. I don't remember. In Unity. Somewhere. In Mono. Oh, Mono Dev. Anyways, let's fix this because I want to leave so bad. I want to go on a walk. It's Saturday, dude. Map pages. If the VA has already taken map pages, doesn't check. Okay, overwrites it. Okay. Now, we need to start. Oh, wait. Not start. UN32T. A for address, and then end for end. Address is VA, right? Oh, I hate cheating. Pages. Get a yeah, okay. Pitch P ground down. P ground down. A is equal to P ground down. To ground it down. Ground down of P ground down of VA, and end is P ground down of VA plus size minus 1. Oh. Wait, what happening? What happening? And while one. Walk table, get PTE, set PT to PA. PA to PTE. Shift right 12 bits, shift left 10 bits. So that means shift right 2 bits. Oh no, not really. You could just do that though. Do I need to shift right? I don't think so. Do I need to shift right? How much? Look at PTE set instruction line. Yeah, I might not be needing to do that. Anyways, we just do if A, let's do ground down, right? If A is equal to end, we break. And otherwise A plus equal to page size. Instead of VA, we do A. Yeah, we do A. Let's just test that. Oh, I'm having a bunch of errors. Page size undeclared. Page size. Page size. Page size. The other error is MMU line 126. There. What is it? Dereferencing the pointer. Where is that? PT Malik and Void. This is Void. You're on 32. What is going on? I'm confused. Anyways, I'm gonna come back to this because the more I push myself, the more tired I'm gonna get, and the worst results I'm gonna get. I just need a break. 2 hours of coding straight. That's pretty good. Thank you for helping me to do that. I was really bored, and this live stream saved me, helped me work more. The course is coming up, guys. If you haven't signed up, go sign up. And it's going to be ready soon, in a few weeks. Not few, like at most 2 weeks. 2 weeks. The first module is going to be ready, and then soon after the second module, by the time you're finished with the first one. So